Two particles can be linked, no matter how far apart they are. They react instantly, like distance doesn't matter. That's quantum entanglement, and it's breaking down our most basic ideas about space. About what space even is. By the end, you'll see a revolutionary idea. That space isn't a fundamental stage. It's an illusion, woven from these quantum threads. We'll start with the first shocking experiments, the ones that proved this spooky connection, then move to the theories, the ones suggesting the whole cosmos, this vast thing, might be a projection from a deeper, entangled reality. So how much of what we see as empty distance is actually a web? A magnificent web of hidden connections. For a long time, that classical view seemed complete. It was a universe built on elegant rules, a silent stage with fixed dimensions, and in that arena, every action had a local cause. A ripple moves through a pond, it pushes the water right next to it, and that influence travels outward at a certain speed. Or a star's gravity, it bends the space around it, and that effect moves at light speed. It's never instantaneous. That principle, locality, it's the foundation of cause and effect. It means no signal, no information, can jump across space faster than light. That speed limit, it's not just a rule, it's the architecture of reality. It keeps events in a logical sequence. Everything has its place, and every influence needs time to travel. That framework gave us a predictable universe, a separable one. Two distant stars or two particles in a lab on opposite sides, they were seen as independent. Their fates weren't linked, that's separability. The universe was a collection of distinct objects inside a container. Not one interconnected thing. Locality and separability, these two ideas, they defined the limits of space. They said what was possible, what was forbidden. They painted a cosmos bound by geometry and causality, a stage where everything follows the script of relativity. And it was a magnificent description. It predicted how starlight bends, the expansion of the universe, even black holes. But then, a revolution started in the smallest places. A quiet, mathematical murmur from the world of atoms and photons began to suggest something unsettling. That this grand classical stage, for all its beauty, might not be fundamental. The first cracks appeared not in the vastness of space, but in the strange behavior of the very small. That microscopic murmur turned into a full rebellion. In the early 20th century, scientists looking at the atom found a world that didn't follow the old rules. Particles like electrons and photons, they weren't just in one place with one property. They could be in a superposition, multiple possibilities at once. Like a spinning coin that's both heads and tails until you catch it and look. That was strange enough. But the real shock, the one that would threaten our whole idea of space, came from a particular kind of quantum link. They called it entanglement. It was so bizarre that even Albert Einstein, who helped discover it, couldn't accept it. In 1935, Einstein and two other physicists, Boris Podolsky and Nathan Rosen, published a famous paper. They weren't trying to prove this weird link was real. They were doing the opposite. They used it as a weapon, a logical argument to show quantum mechanics had to be incomplete. They described a thought experiment. You create two particles that are intimately linked, entangled. You let them fly apart to opposite sides of the lab, or even opposite sides of the galaxy. According to quantum theory, if you then measure a property of one particle, say, its spin, that measurement instantly forces the other, distant particle into the corresponding state. It happens with no signal, no travel time. It just happens. Einstein saw that as impossible. It broke the sacred rule of locality, that nothing can travel faster than light. He called it spooky action at a distance. For him, it was proof that some hidden variables, some deeper layer of reality we couldn't see, must be determining the particles' fates all along. The spookiness wasn't real. It was a sign the theory was flawed. But science has a way of turning criticisms into discoveries. What Einstein proposed as a paradox became a testable prediction. Decades later, physicists like John Bell found a way to check. He created a mathematical theorem that could distinguish between Einstein's hidden variables and the spooky, non-local connection of quantum mechanics. The stage was set for an experiment. In the 1970s and 80s, teams led by scientists like Alain Aspect carried it out. They created pairs of entangled photons and sent them flying off in different directions to detectors many meters apart. The detectors measured the photons' properties at random, so no ordinary signal could coordinate them. The results were clear. The correlations between the distant photons were stronger than any hidden variable theory could explain. They matched quantum mechanics perfectly. The spooky action was real. Information, or at least a correlation, was bypassing space itself, linking 2 points instantly. This was non-locality in the flesh. It wasn't a flaw in the theory. It was a feature of reality. And with that confirmation, the first deep, structural crack appeared in our classical understanding of the universe. The stage, it seemed, had trapdoors. That philosophical puzzle just stayed there for decades, like a ghost in the machine. Then in the 60s, a physicist named John Bell found a way to settle it. He was in Ireland, just at his desk, working with math. He turned the whole debate into something you could actually test. He made a theorem, a kind of litmus test for the universe. It was about an inequality, a specific limit on how correlated two particles could ever be. If the world was what they called locally real, any experiment would stay under that limit. Local realism, that's the comfortable view. It means two things. Realism: particles have definite properties even when you're not looking. They're real objects. And locality: nothing can travel faster than light to change those properties. Information needs time. Bell showed if both those things were true, his inequality would always hold. But quantum mechanics said something else. With entanglement, it predicted correlations so strong they'd break right through that limit. The math was clear. One of these views of reality had to be wrong. You couldn't have both. For years it was just a thought experiment. The technology to do the test properly, to close all the loopholes, it wasn't there. But the idea was planted. Then in the 80s, Alain Aspect and his team in France built the experiment. They made pairs of entangled photons and sent them flying apart to detectors. The detectors measured polarization, the orientation of the light. And they changed their settings at random while the photons were in flight. That was the key. It closed a loophole. No signal at light speed could coordinate the results. The data came in, the correlations were measured, and they violated Bell's inequality. Decisively, the universe had chosen. Local realism wasn't how the world worked. That was a watershed, not just for physics, but for what existence even is. The results told a story. Particles don't have independent properties waiting to be found. Their states aren't separate, and the connection between them doesn't respect distance. It goes right through it. With that proof, a door was open. We had solid ground now to ask a destabilizing question. If two particles, separated by what looks like empty space, aren't truly separate entities, then what is the space between them? What is this vast stage, if the actors on it are linked in a way that bypasses the stage completely? The confirmation of entanglement settled a debate, but it also opened a path. It pointed toward a question that changes everything. If a connection can ignore distance, then maybe distance isn't what we thought. It leads to a radical idea. Space isn't a primary thing. It's not a pre-existing stage. Space is emergent. It arises as a pattern from a deeper network, a network of quantum entanglements. So spacetime isn't a container. It's more like a tapestry, a dynamic tapestry woven from countless threads. And if you cut those threads, the fabric of space might unravel. This turns intuition inside out. The distance between 2 points, the geometry of the universe, becomes a manifestation of entanglement. How entangled two regions are. More entanglement could mean a tighter spatial relationship. It's as if 2 points that are highly entangled in the quantum substrate experience that as physical closeness. And less entanglement might mean greater separation. It might even define the ultimate boundaries. Some theories suggest the surface of a black hole, the event horizon, is where entanglement with the outside stops. The fabric of space reaches its limit there, so the spooky action isn't happening through space. It's what defines space. It weaves the geometry we move through. To see how this could work, you look at the mathematical frameworks. They make this emergence conceivable. They provide the language showing how the collective chatter of quantum links can build the silent expanse of the cosmos. The math for this whole idea about space came from somewhere you wouldn't expect. It was 2013. Two physicists, Juan Maldaisna and Leonard Susskind, they put forward this equation. It looks simple. ER equals EPR, ER, that's Einstein and Rosen. They were the ones who first wrote about these tunnels, wormholes through spacetime. Einstein-Rosen bridges, then EPR, that's Einstein, Podolsky, and Rosen. The same Rosen, actually. They're the ones who found the puzzle of quantum entanglement. And that equals sign in the middle. It's saying these are the same thing. These two ideas from the same people but seeming totally separate. They're describing one phenomenon. A wormhole is the same as a pair of entangled particles. This isn't just a comparison. It's a real proposal from the math of quantum gravity. It means if you have two black holes that are entangled, the space between them isn't just empty. It's connected by a tiny wormhole, a tunnel. Their quantum link has a shape. It has a distance, but it's a shortcut. Imagine two dots on a piece of paper, far apart. The normal distance is a line on the paper. That's our regular space. But if you fold the paper, those dots could touch. The wormhole is that fold. So ER equals EPR says entanglement is the instruction for the fold. The particles aren't signaling faster than light across a gap. In a geometric sense, they're already touching, through a hidden dimension. Their spooky action is just them feeling each other through the tunnel. It turns the problem upside down. The light speed limit isn't broken. It just doesn't apply. You're not moving faster through space. Instead, space itself is made from these shortcuts. The particles are close. Not in our three dimensions, but in the real, entangled geometry of everything. This starts to connect the two big theories that have been separate. Quantum mechanics for the very small, and Einstein's general relativity for gravity and spacetime. ER equals EPR is a bridge. It says quantum information, entanglement, is what writes the code for spacetime geometry. And that opens up a bigger picture. A principle. It suggests everything we see, this whole universe, might be a kind of illusion, a magnificent one. That geometric bridge leads to something deeper about how reality is built. It's called the Holographic Principle. The name is a clue. An ordinary hologram, like on a credit card, is a flat, two-dimensional surface. But when light hits it, it projects a full three-dimensional image. Depth, volume, it all seems to be there. The principle suggests our universe works like that, but more fundamental. All the information that describes everything in a volume of space, every particle, every force, spacetime itself, might be completely encoded on the boundary that encloses it. This three-dimensional world we move through could be a projection from a two-dimensional surface. The whole cosmos might be a cosmic hologram. This idea didn't come from nowhere. It grew from a puzzle about black holes. When something falls into a black hole, it seems to vanish forever. Its information is gone. But that creates a paradox, because quantum mechanics says information can never be truly destroyed. In the 1970s, physicist Jacob Bekenstein and later Stephen Hawking found something. They found a black hole's entropy. A measure of its hidden information isn't proportional to its volume. Instead, it's proportional to the area of its event horizon, its surface. The information a black hole can hold is limited by the size of its skin, not the space inside. That was the first hint. The physics of a region might be described entirely by data on its boundary, so entanglement comes in as the glue. It's what makes the hologram work. The quantum correlations, the entanglements, between countless microscopic parts on that two-dimensional boundary. They generate the illusion of a third dimension. They weave the geometry. It's as if every point inside our world is tied by threads of entanglement to points on a distant, enclosing surface. The more complex the tapestry of entanglement on the boundary, the more detailed and spacious the projected reality appears. In this view, spacetime isn't fundamental. It's a collective phenomenon. It emerges from a vast network of quantum links on a lower dimensional screen. This confronts the classical view of space as a continuous, infinite expanse you could divide forever. Instead, space becomes a derived concept, an approximation. Its existence, its smoothness, its curvature, all of it depends on the underlying quantum data and how it's entangled. There's a fundamental graininess. A limit to how small a region of space can meaningfully be described, because the information describing it is finite. It's stored in pixels on the boundary, and you can only pack so much data into a given area. This forces a reconsideration of what it means for something to exist. Is a star out in the void a real, independent object? Or is it, in the most fundamental description, just a pattern of excited quantum bits on the universe's distant, holographic film? The solidity of the world, the certainty of distance, the very stage for physics, all of it becomes a dynamic illusion, a reality rendered from the quantum information of everything, entangled with everything else. The universe might be a hologram projected from entangled data, but then you have to ask what's doing the projecting. To find that, you don't look out at the cosmos. You look down as far down as you can go. There's a limit to how small space can be divided. The Planck length, it's unthinkably tiny, 10 to the negative 35 meters. A decimal point, then 34 zeros, then a 1. If an atom were the size of our solar system, the Planck length would be about the height of a tree. And at that scale, the smooth stage of physics, it doesn't just get grainy, it dissolves, it becomes chaos, a seething turbulence, quantum foam. Think of the ocean from an airplane. A smooth, blue plane, but down in a lifeboat in a storm it's churning waves, bubbles, spray. Quantum foam is like that, but for reality itself. At the Planck-scale, general relativity, with its smooth, curving spacetime, meets quantum uncertainty. And they collide. The result is violent fluctuation. Tiny wormholes smaller than anything, blinking in and out of existence. Microscopic bubbles of spacetime forming and popping. The geometry isn't fixed. It's a boiling pot. In that realm, here and there lose their meaning. Now and then they blur. Distances become fuzzy. Durations indeterminate. You can't say a point is exactly one Planck length from another, because the space between them is a dynamic storm. So what fuels the storm? Entanglement is a prime suspect. Those virtual particle pairs quantum theory talks about spontaneously popping out of the vacuum. They're born entangled. And just as quickly, they annihilate each other. This isn't a metaphor, it's a constant, frenetic process, happening everywhere, even in empty space. Each of these microscopic events, the creation and instant destruction of an entangled pair, is a tiny knot in the fabric, a momentary warp, and the collective effect of countless trillions upon trillions of these events at every point. That's what might generate the foamy, turbulent structure of spacetime at its foundation. The smooth stage we see is an average, a statistical calm that only emerges when we zoom out from the quantum frenzy, like the ocean looking flat from high above. Our classical, measurable space is an illusion of scale, a calm surface over a deep, chaotic quantum sea, which means the geometry of the universe from the smallest wormhole to the shape of a galaxy it isn't written in stone. It's written in activity, in the ceaseless dance of creation, entanglement, and annihilation, happening at the absolute foundation of everything. To see what this turbulent genesis builds, you have to pull the camera all the way back. From the quantum foam to the cosmic scale, where the structure of the entire universe might hold the signature of its entangled origins. From that quantum foam, a structure emerged. The early universe's microscopic chaos didn't stay small. Right after the beginning, something called inflation happened. The universe expanded faster than light. It stretched those first quantum fluctuations, tiny wrinkles in reality, to an enormous scale. A tremor smaller than a particle became the seed for a galaxy cluster. That's a central idea now, but there's more. Those first fluctuations weren't just random. They were probably entangled. The quantum connections that define space were woven in at the very start, and then stretched across everything. When we look out now with our best telescopes, we don't see a uniform scatter. We see a web, a vast cosmic architecture. Long, delicate filaments of galaxies, millions of light-years long, meeting at dense nodes where thousands of galaxies swarm. And between them, huge voids, caverns of near-nothingness, hundreds of millions of light-years across. That's the large-scale structure, its grand design. And that design, many think now, is a direct projection of those first quantum seeds. The pattern of the cosmic web where filaments form, where voids open, might be a kind of fossil. A fossilized imprint of quantum entanglement from the dawn of time. In the early, hot, dense universe, particles and energy were in constant, intimate interaction. They were all connected, entangled. And when inflation blew up the universe, it didn't just stretch distances. It stretched those connections. It took the quantum links between neighboring points and pulled them across vast reaches. The spooky links that once existed at a subatomic scale were written, in a transformed way, onto the distribution of matter itself. So the galaxies we see on opposite sides of a void aren't truly independent objects that just happen to be there. Their positions, their existence in those specific spots, might be the end result of a correlation established when the universe was smaller than a proton. The cosmic web isn't just a structure in space. It is a structure of space, and its blueprint was drawn by quantum entanglement. Now, the entanglement between two individual galaxies today is immeasurably weak, drowned out by eons of history. But the large-scale statistical pattern, the architecture itself, retains the memory. It challenges the old view that the cosmos is purely classical, that once things got big, quantum weirdness just washed away. Instead, it suggests quantum physics didn't just start the universe, it shaped it. The rules of the very small left their signature on the very large, connecting the quantum genesis to the galactic structures we see. That takes us from the foam to the web. But to really test this idea, we have to look to where space itself is stretched to its breaking point. The cosmic web is this vast imprint of ancient quantum links. But in some places, those links get stretched, almost to the breaking point. At the edge of a black hole, space itself faces a test, and information faces a test. This is where entanglement runs into a paradox. The rules are clear. Quantum mechanics says information can never be truly destroyed. The data that defines a particle, or a book, or a star, it can be scrambled. It can be transformed, but it can't be erased from reality, and then you have black holes. Black holes seem to break that rule. When something falls in, it passes the event horizon. The point of no return, it vanishes. According to Einstein, to general relativity, it gets crushed into the singularity, and that's that. But then, in the 1970s, Stephen Hawking found something. He found that black holes aren't completely black. Because of quantum effects right at the edge, they leak a faint glow of particles, Hawking radiation. And over immense time, this radiation makes the black hole lose mass, shrink, eventually evaporate completely. So here's the problem. If the black hole evaporates, what happens to all the information that fell in? The Hawking radiation looks random. It doesn't seem to carry any details about what made the black hole. It's like burning a library. The heat and light come out, but the words are gone. That's the black hole information paradox, a direct conflict. Quantum mechanics says information is preserved. General relativity suggests it's lost. The potential solution brings us back to entanglement. The Hawking radiation isn't just random heat. Those particles are born from quantum activity at the event horizon. They are created in pairs. One particle falls back in, the other escapes as radiation, and these two particles are entangled. So the escaping radiation is entangled with the interior of the black hole. As more radiation escapes, the interior becomes entangled with a growing cloud of particles outside. And this is where things get tangled. A new paradox emerges. For information to be preserved, the escaping Hawking radiation particles have to eventually become entangled with each other to form a coherent record of what fell in. But quantum mechanics has this rule: monogamy of entanglement. A particle can be deeply entangled with one partner, or with a group in a specific way. But it can't be maximally entangled with two different systems at the same time. The radiation particle escaping today is entangled with its partner that fell in long ago. For the information to come out, that same escaping particle must also be entangled with radiation that escaped yesterday. It seems to be doing double duty, which violates the monogamy rule. The proposed fix for this violation is shocking. It suggests that at the event horizon, there's a literal wall of fire. A firewall of unimaginable energy that would incinerate anything crossing it. This fixes the math by severing the old entanglement, but it creates a huge problem for general relativity, which says falling through the event horizon should be uneventful. You shouldn't feel a thing until tidal forces pull you apart much later. So we have a paradox within a paradox, the Firewall Paradox. Resolving this isn't about choosing one theory over the other. It's a sign that both pictures are incomplete. The likely answer is we need a new understanding, where spacetime itself, including the inside of a black hole, isn't a pre-existing stage. It's built from entanglement. In this view, a black hole isn't just an object sitting in space. It's a dynamic knot in the fabric of reality, where the quantum threads of entanglement are woven into an extreme geometry. The event horizon isn't a sharp boundary in empty space. It's a surface where the pattern of entanglement with the outside world fundamentally changes. The information isn't lost inside a pit. It is encoded on the horizon itself, in the way it is entangled with the Hawking radiation. The evaporation of a black hole might then be seen not as a destruction, but as a transformation. A translation of information from one form to another, from a knot of spacetime into a cloud of entangled radiation. This tension at the edge of a black hole is more than a puzzle about a strange object. It's a glaring signal. A signal that to understand the most extreme places, we have to accept that space and time and information are all facets of a deeper quantum reality. Black holes force the issue. They show the two great pillars of physics can't both be right. Not as they are. On one side, there's general relativity, the theory of the very large. It describes gravity, but not as a force. It's the curvature of a stage, a smooth, continuous stage. Space and time are woven together. A flexible fabric. Massive objects bend that fabric. It's a geometric picture, a beautiful one. On the other side, there's quantum mechanics, the theory of the very small. It's a world of probability. Particles exist in clouds of possibility. They can be linked, entangled across any distance. It's a world of discrete jumps. Fundamental uncertainty, and here's the conflict. General relativity needs space to be smooth, continuous. Quantum mechanics needs it to be grainy, probabilistic. They are incompatible, mathematically, philosophically. You can't just combine them. In the heart of a black hole or at the first instant of the Big Bang, both theories should apply. And when you try to use them together, the math breaks. It produces nonsense, infinite densities. It's a sign. Our description of reality is incomplete. This isn't just a technical problem. It's a crisis for our understanding of existence, because space and time are the arena for everything, and we have two contradictory rulebooks for that arena. We are fundamentally lost. The quest to resolve this is the search for a theory of quantum gravity, a single framework, one that can describe the force that shapes the cosmos and the particles that inhabit it. And in that search, entanglement is no longer just a curious feature. It's becoming the central clue. In Einstein's geometric universe, there's no natural place for spooky action. The connection is severed, but if entanglement is real and we know it is, then the geometry must emerge from it, not the other way around. This shifts the entire goal. The task is to build geometry from entanglement. Several paths are being forged. String theory proposes the fundamental ingredients aren't point-like particles. They're tiny, vibrating loops, strings. Their different vibrations give rise to all the particles and forces. And in this view, spacetime itself is secondary. It emerges from the collective behavior of these strings, from how they're linked. Entanglement between strings could be what stitches the smooth fabric of space together. Another path is loop quantum gravity. It suggests space itself is not continuous. It's woven from a network of tiny, discrete loops, a fabric made of individual threads. The geometry of the universe comes from how these loops connect, how they intersect, and here, too, entanglement is fundamental. The quantum links between these loops define their proximity. Their geometry, they are the ties that bind the network into the shape we experience. Then there are other approaches, like the idea of spacetime as a quantum error-correcting code. A stunningly different perspective. It suggests the three-dimensional world is a protected projection. Information is stored redundantly on a two-dimensional boundary. Entangled in a clever way, so it can withstand errors, like the universe having built-in backup systems. The solidity we see, the locality, it's an illusion. Created by this cosmic error correction. In all these frameworks, the classical stage of space is an approximation, a useful illusion. It works perfectly well for everyday life, for planets and stars, but when you probe to the absolute limit, set the Planck-scale inside a black hole at the beginning of time, that illusion shatters. The smooth continuum dissolves into a buzzing network of quantum relationships. Space is not a container things are in. It is a manifestation of how things are connected. This means the very thing we thought was most fundamental, the arena itself, is threatened, it is demoted. It emerges from something deeper, more abstract, profoundly interconnected. The journey to understand this is more than physics. It is a reimagining of what is real. The search for quantum gravity, it leads to a new language. Physicists are turning to the science of information itself. Quantum information theory. It's not just a different set of equations, it's a different way of thinking. In this view, entanglement isn't just a spooky phenomenon, it's a resource, a form of pure correlation you can quantify like a currency. You can store it, spend it, send it. That's the basis for ideas like quantum teleportation, where you transfer a particle state across space using a shared entangled link. But the implications go further. They reach into the architecture of reality. If space emerges from entanglement, then you need a way to measure the entanglement between different parts of the universe. That measure is called entanglement entropy. It sounds technical, but the idea is profound. It quantifies how much information one region of a quantum system shares with another, how deeply their fates are intertwined. You can calculate it between, say, the inside of an imaginary sphere and the outside. And what you find is startling. The amount of entanglement isn't proportional to the volume of the sphere. It's proportional to the area of its surface, the boundary. This echoes exactly the formula for black hole entropy from Jacob Bekenstein and Stephen Hawking. A black hole's information content is defined by the area of its event horizon, not its volume. This isn't a coincidence, it's a clue. The fabric of space seems to be woven from quantum information, and the threads are visible only at the boundaries. The connection between two regions, their apparent distance, their geometric relationship is dictated by the pattern and strength of the entanglement between them. More shared information means a tighter, more direct connection in the geometry that emerges. Less entanglement means greater separation. This transforms the entire conception of physics. We're shifting from a world view where things exist in space and interact through fields, to a worldview where the fundamental stuff is information, correlated information. And what we perceive as space, with its distances and curvature, is just the most efficient way to organize those correlations. It's as if the universe is a vast, dynamic network. A cosmic internet. The nodes aren't computers, but fundamental quantum degrees of freedom, and the links between them, the bandwidth, is entanglement. The geometry we experience, the fact that your screen seems to be a certain distance from your eyes. That's the user interface. A simplified, classical projection of an unimaginably complex quantum data structure. It's a profound shift. It suggests that to ask what is space made of is to ask how is quantum information shared. The stage is dissolving into the script. And the script is written in a language of connection, not separation. These radical ideas need a test. If space is made from entanglement, you should be able to see the seams. So how do you run an experiment on reality itself? The challenge is huge. We can't probe the Planck-scale. We can't reach into a black hole, but science builds bridges. From the possible to the profound, enter the quantum simulator. It's not a computer. It's a universe in a box, a simplified one, meticulously controlled. Scientists use arrays of ultra-cold atoms, trapped by lasers, cooled near absolute zero, or grids of superconducting loops, qubits in cryogenic chambers. In these environments, you can engineer quantum states. You can program patterns of entanglement into the system, create a lattice, a network, each node linked to its neighbors in a specific way. A tunable way. The goal is to see if, by manipulating these quantum links, the system behaves as if it has geometry, as if it has curvature. In a flat, cold lab, could a synthetic black hole emerge from the math of entanglement? Early results are suggestive. In some experiments, when entanglement is arranged in a certain pattern, the collective behavior of the atoms follows equations. Equations that look exactly like the ones for a particle moving in a curved space. The simulator hasn't created real gravity, but it has created a model where the experience of geometry emerges from quantum connection. It's a powerful analogy, a working demonstration. The other frontier is the sky itself. We're looking for the universe's own experiments, written in light and gravity. The cosmic microwave background, that ancient afterglow of the Big Bang. It's a fossilized snapshot of the infant universe. If quantum fluctuations entangled with spacetime geometry seeded the large-scale structure, there might be fingerprints. Subtle statistical fingerprints left in this background radiation. Anomalies in its polarization patterns, for instance, that could be a signature of primordial gravitational waves. Ripples from the quantum foam of inflation. Finding them would be indirect evidence, but monumental. Then there are gravitational waves. When two black holes collide, they shake the fabric of spacetime. They send out ripples we can now detect. The detailed shape of these waves encodes information about the nature of spacetime itself. Some theories of quantum gravity predict tiny deviations in how these waves propagate, a kind of spacetime foaminess that might slightly scatter or delay different frequencies. Our detectors aren't sensitive enough yet. But they are improving. Each new collision is a message, and we are learning to listen for the quantum accent in its tone. This is the crucial pivot. From philosophy to physics, from what if to what is. These experimental paths in labs and in observatories seek to turn a beautiful metaphor into a measurable fact. They aim to catch reality in the act of constructing itself, to show that the stage is not just where the play happens, it is the play. The experimental quest brings us back to a fundamental question about reality. When entanglement rewrites the rules of space, it's not just changing physics. It's challenging our deepest assumptions about existence. For centuries, Western thought has been built on a foundation of separateness. The universe as a collection of distinct objects, a rock here, a star there, independent entities existing in their own right, located in an absolute container called space. That view is called local realism. It's a powerful, intuitive way to see the world. But quantum entanglement declares it an illusion. The particles in those experiments aren't separate things acting on each other across a void. Their identities are intertwined. To describe one, you have to instantly reference the other. No matter the distance, they're not two, they are one system. That's non-separability. The universe, at its core, might be fundamentally holistic. A single, interconnected quantum reality that we, with our classical senses, break apart into the illusion of separate pieces. So the limits of space aren't physical walls at the edge of the cosmos. They're the limits of our perception. The boundaries between here and there are useful approximations, but they are not fundamental. Distance becomes a relational property. It emerges from the pattern of connection. 2 points are far because they share little quantum information. They're close because they're highly entangled. The space between them is a description of their relationship, not a pre-existing emptiness. This perspective finds an echo in various schools of Eastern philosophy. The idea of an all-pervading unity, that separation is Maya or illusion, that the true nature of reality is an undivided whole, and physics, through the hard language of mathematics and experiment, is arriving at a similar vista. Not through mysticism, but through measurement. The implications ripple far beyond the lab. It touches how we understand identity and consciousness. If particles have no independent existence, what does that say about us? We are made of particles. Are we isolated minds in separate bodies? Or are we, in some subtle quantum sense, nodes in a vast, conscious network? These are open questions. But the framework invites them. It suggests our feeling of separateness from the world, from each other, might be the classical view asserting itself. A powerful, convincing illusion built from our scale and our senses. The quantum view offers a different metaphor. The cosmos is not a collection of things. It is a web of relationships. We are not merely inhabitants of space. We are expressions of the connections that weave space itself. That shifts the focus from objects to the links between them. From nouns to verbs. The universe is less like a static sculpture and more like an ongoing conversation. A dynamic, entangled dialogue from which everything, including the stage it plays out on, continuously emerges. To accept this is to see the world anew. The empty sky is not empty. The vast distances between stars are not voids. They are a living geometry, a tapestry of latent connections. Every part of the cosmos holds a silent, spooky link to every other part. A connection written not in light, but in the quantum code from which light and space and time are born. That silent connection in the cosmos seems to ignore the universe's most famous rule. Nothing can travel faster than light. It's not a suggestion, it's a law. The cornerstone of Einstein's relativity. It defines causality. Cause comes before effect. It's the speed limit of reality itself, and yet, entangled particles appear to laugh at that limit. You measure one, and its partner knows. Instantly, across a lab, across the planet, the correlation is immediate. No travel time. It looks like information has jumped the gap faster than light. That's the direct threat. It feels like a violation, a loophole in the architecture of everything, but there's a crucial caveat. The detail that saves Einstein's law for our everyday world. You can't send a message this way. You can't control the outcome. When you measure your entangled particle, the result is random. It might be spin up or spin down. You can't force it to be up to mean yes. Your friend, holding the partner far away, will see their particle snap into the opposite state instantly. But from their perspective, they just see a random result. They have no way of knowing if your measurement caused it, or if it just happened by chance. Without a pre-arranged code, and without your ability to control the signal, no meaningful information is transmitted. You can't send a faster-than-light text. That's why physicists call it quantum non-locality, not superluminal signaling. It's a correlation without communication. A shared secret written at the moment of their creation, not transmitted across the distance. So relativity stands unbroken for all practical communication. The cosmic speed limit is safe, but the philosophical implications are seismic. The instantaneous correlation itself tells a different story. It suggests the underlying reality connecting these particles operates outside the spacetime framework. The speed of light governs motion through space and time. But if the particles aren't truly separate entities moving through space, then what is traveling? Their connection isn't a signal racing through the void. It's a single fact about a unified system manifesting in two places at once. The limit doesn't apply because nothing is crossing the distance. The distance, in a profound sense, might be part of the illusion. This doesn't break relativity. It implies spacetime is not the ultimate arena for all physical processes. There's a deeper layer, a quantum substrate, where relationships are primary. In that layer, the concepts of here and there are not fundamental. The correlation is just a property of the whole. It's like having a pair of gloves. You put one in a box and send it to Mars. When you open your box on Earth and find a left-handed glove, you know instantly, without any signal from Mars, that the glove there is right-handed. The information wasn't sent. It was always a fact about the complete set. Entanglement reveals that particles at their quantum heart are like those gloves. Their properties are defined relationally from the moment they are paired. So the speed of light limit remains the iron law for anything moving through the stage. But entanglement suggests the stage itself is not fundamental. The actors are connected by the script, not by the footlights. That realization forces us to separate two ideas we thought were inseparable: the geometry of spacetime and the foundation of physical reality. One is a magnificent, emergent structure. The other is a web of quantum connections that does not play by its rules. And if that web is the true foundation, then we have to ask what other cosmic laws might be emergent. What else is merely a feature of the stage and not a rule for the players? The speed of light controls how things move on the stage, but entanglement suggests the stage itself isn't the most basic thing. It's a structure that comes from something else. And that leads to something even more personal: the flow of time. We feel it as this one-way river. The past is fixed. The present is just a moment. The future is open. That arrow of time feels as basic as space. But if you trace it back to where it comes from, you find it might also be made from quantum threads. Our strongest arrow of time comes from thermodynamics. It's the idea that disorder always increases. Entropy always goes up in a closed system. An ice cube melts in a warm room. Its orderly structure scatters. It never just refreezes from the puddle on its own. That movement from order to disorder gives time its direction. But then you have to ask, what created that initial order? Why does the universe always move toward more disorder? And here, entanglement provides a link. The increase of entanglement between systems over time is mathematically tied to the increase of entropy. Think about two boxes that were separate. One has hot gas, the other has cold gas. At the start, they have little quantum correlation, they're independent. But then you open a window between them, the gases mix, the temperatures equalize, and during that process, the particles from one box become entangled with particles from the other. Their fates get correlated in a complex web. The system has become more disordered, and it has also become vastly more entangled. The growth of entanglement and the growth of entropy, they march together. Now take that and scale it up to the whole cosmos. The early universe was in an extremely ordered state. Low entropy. A hot, dense, remarkably uniform soup. From that pristine starting point, it's been evolving for billions of years. Galaxies formed, stars ignited and died. Countless interactions happened. With each interaction, quantum correlations spread. Entanglement proliferated, weaving an ever more complex tapestry of connection across everything. Some theories suggest this relentless growth of entanglement is what creates our clear, classical sense of time. The progression from a past with less entanglement to a future with more entanglement that defines the arrow. This flips the intuitive picture. We don't move through time because time is a pre-existing dimension. Instead, our experience of time emerging, of one thing after another, comes from the universe becoming more interconnected. The now we feel might be the process of new quantum correlations being established, locking possibilities into definite outcomes. The fixed past is a record of correlations that have been created, and they can't be undone. The open future is the realm of possibilities not yet entangled into the universal web. At the most fundamental quantum level, time might not flow in a simple linear way. Without widespread entanglement, the distinction between cause and effect could blur. In a hypothetical, perfectly isolated quantum system with no new entanglements, the idea of before and after could lose its meaning. It's the relentless interaction and correlation of quantum systems, from particles in a lab to dust in a nebula, that builds the robust, classical timeline we live in. So entanglement doesn't just threaten the spatial stage. It challenges the entire spacetime continuum. The four-dimensional block of classical physics, with its unambiguous timeline, is an emergent property. A grand illusion that solidifies from the quantum fog as systems interact and correlate and become inextricably linked. Our journey from birth to memory, the very feeling of duration, might be the human-scale sensation of the universe knitting itself together. Through an infinite web of quantum handshakes. The emptiness of space is a lie. That void between galaxies, the blackness that goes on for millions of light years classically, it's nothing. A perfect vacuum, just a backdrop. But quantum theory says something else. That void is alive, it's a seething sea. An ocean of potential, that's the quantum vacuum. And it's not empty. It's the ground state of reality and it's buzzing. Because of the uncertainty principle, empty space can't be perfectly still. At every point, for the briefest moments, pairs of virtual particles and antiparticles just appear. They borrow energy from the vacuum, exist for an instant, and then annihilate, giving the energy back. This isn't a metaphor. It's a continuous process, happening everywhere all the time. And there's a crucial detail here. These virtual particle pairs, they aren't born independent. They're created entangled. From the moment they flicker into being, their quantum states are linked. One spin is opposite the others. Their fates are correlated. So every tiny point in the cosmos is connected to its neighbors by this flickering web of ephemeral entanglements. A dynamic network of ghostly links, forming and dissolving faster than we can think. That means the vacuum itself is a medium, a quantum-connected medium. Its apparent stillness is just a statistical average of unimaginable turbulence. The energy of this perpetual motion is real. It's called zero-point energy. And it has a staggering consequence. This vacuum energy, this energy of nothing, might be the engine behind the accelerating expansion of the universe. It's the leading candidate for what physicists call dark energy, the cosmological constant, the force that's pushing galaxies apart faster and faster. So the emptiness that seems to separate things isn't a neutral gap. It's an active participant. Its inherent quantum activity, sustained by all those entangled pairs, generates a repulsive pressure. And that pressure shapes the fate of everything. The classical idea of space as a passive stage, an inert container, it collapses. The vacuum isn't a blank canvas. It's the canvas and the paint and the painter all at once. Its properties, its energy, its expansion, its very notion of emptiness, are all sustained and defined by the quantum phenomenon of entanglement. The space between stars isn't a void you could cross to find true nothingness. It's a plenum, a fullness, a living geometry woven from transient quantum threads. That erodes the last vestige of the classical backdrop. There is no passive background. There's only an active, interconnected quantum field. And from its endless dance, the illusion of serene, empty space emerges. If space comes from quantum connections, then the whole story of the cosmos has to start differently. We've always talked about the Big Bang, a moment of extreme density and heat, where everything began to expand. But entanglement changes that picture. The Big Bang wasn't an event happening inside some empty space. It was the moment space itself formed. So before geometry, what was there? The main idea is a pre-geometric quantum state. A place with no distance, no location, no dimensions you could move through. In that first state, the basic ingredients weren't particles. They were quantum correlations, just a chaotic potential for connection. A state of maximum entanglement where everything was linked to everything else. One whole thing. So the birth of the universe might be a process of disentanglement, or really, a reorganization of how things were entangled. As this quantum network went through a phase change, those intense, all-to-all connections started to specialize. To become local, the quantum links that once connected everything directly got stretched. They got channeled, and that created the first distinctions. Here from there, this from that, and with those distinctions, distance emerged. It was just a way to describe the new pattern of connections. Then you have inflation. That rapid expansion in the first instant. It takes on a new meaning. It wasn't just space stretching. It was the quantum tapestry of that pre-geometric state being pulled taut. The initial quantum fluctuations, the seeds for all galaxies, were themselves entangled correlations. Inflation magnified them. It imprinted that quantum signature onto the geometry of the new cosmos. The vast space we see now is the fossilized imprint of that ancient quantum network, stretched to a cosmic scale. This changes the narrative of our origins. We aren't just the aftermath of a physical explosion in a void. We are the expression of a quantum relationship becoming geometry. The existence of space itself is a testament to a fundamental shift in how reality is connected. It means quantum correlation isn't a side effect of the universe. It's the foundation, the stage the universe emerged from. The quantum vacuum is this field of potential. And we're starting to paint with it. We can create entanglement now, manipulate it. It's not just about studying reality anymore, it's about building with it. This is a shift, a technological shift, where quantum correlation becomes a tool, not just a strange effect. Quantum computers are at the center of this. They don't use bits like a regular computer. Bits are 0 or 1, they use qubits. A qubit can be 0, 1 or both at the same time, that's superposition. But the real power is when you entangle them. You link multiple qubits together. Their states become connected. It creates this web of possibilities. And that lets a quantum computer explore many answers at once. It can solve problems a classical computer couldn't finish in the age of the universe. It's applying that quantum weirdness to process information in a new way. Then there's quantum cryptography. It offers a different kind of security. Take two people, Alice and Bob. They share a pair of entangled particles. They can use that link to make a secret key, to encrypt messages. And the key point is if someone tries to eavesdrop to intercept the key, they disturb the entanglement. Alice and Bob would know, it's not just secure. The security is based on physics, on the laws themselves. This is being tested now in limited networks. It's a look at a future with private communication. The bigger idea is a quantum internet, a global network, but it wouldn't just send data. It would distribute entanglement itself. Not for faster-than-light messages, you can't send a signal that way, but to create ultra-secure connections, and to link distant quantum computers into one more powerful processor. The groundwork is happening now with special fiber optic cables and satellites that can send entangled photons across continents. Every transmission is an experiment in keeping a fragile quantum link intact across the chaos of the world. And by doing this, we're learning to engineer these correlations, the same correlations that might be the stitches in space itself. The line between information technology and fundamental physics gets blurry here. Our control over entanglement is like a workshop for cosmology. By learning to create these states in the lab, to sustain them, to measure them, we're developing the tools to ask better questions about the universe. Could a civilization, far more advanced with a deep mastery of entanglement, learn to read the geometry of spacetime? Could they probe a black hole's interior? Not with a probe, but by analyzing the entanglement in its Hawking radiation. These are speculative thoughts. Distant ones, But the path starts here. In our labs, we're taking the first steps, from observing quantum spookiness to actively weaving it into tomorrow's technology. Trying to build a quantum network is, in a real sense, a rehearsal for understanding the network that space itself may have come from. This mastery of entanglement in the lab, it comes with a profound irony. Our most advanced tools for probing reality, they're constrained by the very principles they're built to test. Measuring an entangled system disturbs it. You can't peek at the quantum world without leaving a fingerprint. And that's more than a nuisance, it's a fundamental limit. When we try to measure the correlation between two particles, our intervention changes the system. We force a definite outcome. We collapse the superposition, and we often break the very entanglement we wanted to study. So we only ever get a partial picture. A statistical picture of the quantum connections that might underpin space. We see the shadows on the wall, not the object casting them. And the challenge gets more extreme when we aim for the ultimate resolution. To directly observe the quantum foam, the turbulent structure of spacetime at the Planck scale, we would need a particle accelerator the size of our galaxy. For all practical purposes, that's forever beyond our reach. We're like astronomers trying to read the date on a coin from the surface of a distant star. The scale is too small. The energy required is too great. So science is forced into a position of inference. We have to look for echoes of that fine-grained structure in phenomena we can measure. The subtle scattering of light from distant quasars, the precise timing of gravitational waves. The evidence is always indirect, a whisper of the storm heard from a great distance. Our cosmological view is bounded in a similar way. We live inside a cosmic bubble, the observable universe. Its boundary is our particle horizon. The farthest distance light has had time to reach us since the beginning. Everything beyond that horizon is, by definition, unobservable. We cannot see it. No signal from it can ever reach us. That creates a fundamental limit to our knowledge. If the structure of space emerges from a global pattern of entanglement, we can only ever study the portion of that pattern inside our bubble. We're trying to understand the design of a tapestry by examining a single, frayed corner. The full pattern may be forever hidden. These aren't just practical hurdles, they're epistemic walls. They define the boundary of what is scientifically knowable. The threat entanglement poses to our classical concept of space. It's mirrored by a challenge to the limits of human knowledge itself. Some questions about how reality is woven at its deepest level may stay in the realm of elegant theory. Supported by compelling but indirect evidence, we're forced to become cosmic detectives, piecing together a story from clues that are fragmented, distorted, incomplete. This realization isn't a defeat. It's a reorientation. It shifts the goal from a complete, direct picture of the quantum foundation to building the most coherent story from the clues we have. It means accepting that the universe may hold layers of truth that are, by their nature, partially veiled from our instruments and from our intuition. The journey to understand space becomes a humbling lesson in the limits of observation, a reminder that the greatest mysteries are often those that define the very edge of the knowable. Where science meets the profound silence of the cosmos, our tools might be limited, but the questions we can ask aren't. With entanglement, physicists have put forward different interpretations, different stories for what's really going on, and these aren't just technical disagreements. They're completely different visions of reality, and each one deals with the threat to space in its own way. Take the many worlds interpretation. Hugh Everett proposed it in the 1950s. It gives a very simple answer to the measurement problem. In this view, the wave function doesn't collapse randomly into one outcome. Instead, every possible outcome of a quantum event actually happens. The universe splits. It branches into multiple copies, one for each possibility. So when you measure an entangled particle and find it spin up at that moment, the universe divides. In one branch, you see spin up, and your distant partner's particle is spin down. In another, parallel branch, a version of you sees spin down and the partner is spin up. Both realities exist side by side. From here, entanglement isn't some spooky link across our space. It's a correlation between these parallel branches. The particles aren't communicating across a gap in our universe. They're connected because their fates are part of the same branching structure, a much larger, higher dimensional reality. The action at a distance disappears because in the full multiverse, everything that can happen does happen. The randomness we see in our branch is just our limited view of a vast, deterministic tapestry of possibilities. Space in our individual branch stays local and classical. The weirdness gets pushed out into an unseen landscape of other worlds. Then there's Bohmian mechanics, pilot wave theory. It goes the opposite way. It says particles are real, point-like objects. They have definite positions at all times, but they are guided by a hidden wave, the pilot wave that fills all of space. This wave is non-local. It reacts to everything everywhere instantly. When you measure one entangled particle, the pilot wave updates instantaneously. It steers the other particle into its correlated state, no matter the distance. Here, non-locality is explicit. It's built right into the law of motion. Space is still a container, but the things moving in it are connected by a field that ignores the container's local rules. The stage is intact, but the director is giving instructions from somewhere that doesn't care about the stage's geometry. Other interpretations, like quantum Bayesianism, take a different angle. They suggest quantum states, including entanglement, aren't objective features of the world. They are descriptions of an observer's knowledge, their beliefs. In this view, the puzzle of space isn't in the particles. It's in the limits of our information. The spooky connection reflects a Bayesian update in our understanding when we learn something about one part of a system. What's remarkable is that all these wildly different stories, from splitting universes to hidden waves to subjective knowledge, they all make the same experimental predictions. They all agree on the math of entanglement, and they all, in their own way, say that our classical, separable notion of space is inadequate. It can't be the whole story. Whether the solution is to embed our space in a multiverse, or to fill it with a non-local wave, or to rethink probability itself, the conclusion is the same. The intuitive arena of our daily life is a simplified picture. Exploring these frameworks isn't about finding which one is true. Not yet, anyway. It's about stretching our imagination. It shows the threat to space isn't a single, simple problem with one answer. It's a profound puzzle. It forces us to question the nature of existence, of causality, of what it means to be real. Each interpretation is a different lens. Through each one, we see a different facet of the same dazzling, mysterious gem. The strangest connections don't come from being close. They can be made by someone else, between strangers who have never met. That's entanglement swapping. It feels like a trick. You start with two separate pairs of particles, pair A and pair B. The particles in pair A are entangled with each other. The particles in pair B are entangled with each other. But there's no link between pair A and pair B. They are independent. Then you take one particle from pair A and one from pair B. You bring them together to a central station. You don't measure them individually. You do a special joint measurement on them, a Bell state measurement. That measurement doesn't tell you anything about either particle's own state. It tells you how their states are correlated. And something happens. At that instant, the two remaining particles, the ones you never touched, the ones still far apart, they become perfectly entangled with each other. The original links are cut. A new link is made across the gap. It's like introducing two strangers by showing them a photo of their mutual friend. Suddenly they share a bond. The connection wasn't transferred through space. It was revealed or enforced by an act of measurement that reshuffled the whole quantum description. This protocol shows something. Entanglement isn't a force, it's not a signal. It's not a thread of energy you can trace from point A to point B. It's a statement about the whole system. A correlation written into the quantum state itself. The particles in swapping don't need to be close. The two that end up entangled could be on opposite sides of the planet. Their new relationship has nothing to do with the distance between them. It has everything to do with the information that now describes them as a single, non-separable thing. This is more than a lab curiosity. It's the operational heart of building a quantum internet. Entanglement swapping is the core mechanism for quantum repeaters. Devices that will extend these fragile quantum links across continents. By creating entanglement in segments and then swapping to connect them, we're engineering the universe's method of connection. And conceptually, it's a blow to classical intuition. It shows that the quantum links which may define the geometry of space are themselves unbound by geometry. They are more fundamental, more abstract. They belong to a layer of reality where interaction and proximity aren't prerequisites for a deep, instantaneous bond. The stage of space emerges from these connections, but the connections themselves play by a different set of rules, written in the language of pure information. The bonds between atoms give a solid its shape. That's a familiar reality. Individual atoms don't have rigidity. They don't have a fixed form. But when you bring trillions of them together, linking them through chemical bonds, something new emerges. A table, a mountain, a planet. The collective behavior creates a property solidity that wasn't there in the parts. This is an analogy, but a powerful one for spacetime. Think of the fundamental quantum units, whatever they may be, as the atoms of reality. Individually, they have no geometry, no sense of here or there. But when these units become entangled with one another, when they form a vast, interconnected network of quantum bonds, a collective property emerges from their correlations. That property is the smooth, continuous fabric of spacetime itself. The entanglement is the glue. It's what binds the quantum points into a cohesive, extended geometry. Just as the bonds in a crystal lattice determine the shape and strength of the material, the pattern of entanglement between quantum degrees of freedom could determine the curvature and connectivity of the cosmos. This shifts our perspective dramatically. We're used to thinking of space as the container, and then things within it become linked. But this analogy inverts that. The linking comes first. The entanglement is primary, and what we perceive as space is the secondary, emergent structure that arises from it. It's the macroscopic texture of a microscopic web. Now, consider what happens if you weaken that glue. In a solid, if you sever enough atomic bonds, the material cracks, it changes shape, it might even fall apart. In the spacetime analogy, disentangling regions cutting the quantum threads between them wouldn't just separate 2 points. It could fundamentally alter the topology of space. It might create a boundary where there was continuity. This is where black hole horizons find a potential explanation. The event horizon could be seen as a surface where the entanglement between the interior and the exterior drops to nearly zero. The quantum glue holding that region to the rest of the universe has been stretched and severed. The interior becomes its own, isolated patch of the quantum network, disconnected from the web outside. The space inside isn't gone, but its connection to our geometric reality is. This visualization helps make sense of a profound idea. A property of pure correlation of shared information at an unimaginably small scale can produce the most fundamental experience of all, the experience of living in a connected, three-dimensional world. It suggests that without this ubiquitous quantum glue, without the endless hum of entanglement linking every point to every other point, space as we know it would not exist. There would be no stage, just a scattering of unconnected possibilities. The solid ground beneath our feet and the vast emptiness between the stars are two expressions of the same phenomenon. They are the geometry that whispers of the quantum bonds from which everything is woven. The classical universe had this safety feature, the cosmic censorship hypothesis. Roger Penrose proposed it. It was about the limits of predictability. In general relativity, you have singularities, points where space-time curvature becomes infinite. The laws of physics break down there, and the idea was that nature would always hide them. A naked singularity couldn't exist. It would always be cloaked behind an event horizon. So a black hole's singularity is sealed away. The horizon protects the outside universe. It keeps that lawless physics from influencing our predictable spacetime. It maintains order, a firewall of invisibility, but then quantum entanglement comes in, the Firewall Paradox. It throws a wrench into that. The debate about the horizon, whether it's calm or a wall of fire, that directly challenges cosmic censorship. If the horizon becomes violent to resolve the information paradox, then the singularity isn't the only threat. The horizon itself becomes where classical physics fails. The protective veil becomes a destructive inferno. That doesn't just expose the singularity, it transforms the entire boundary. The censorship would be broken. Not by revealing the core, but by making the doorway itself impassable. So the question is how the universe keeps its smooth, classical appearance, with all that quantum turmoil. The answer might be in the thing causing the trouble, entanglement itself. We might need a quantum version of cosmic censorship, where it's not a geometric horizon that hides the singularity, but the structure of quantum information that regulates spacetime. In that view, the entanglement between the black hole interior and the Hawking radiation outside, it doesn't create a firewall. It arranges itself in a clever way, so that to an outside observer, the horizon looks perfectly smooth and empty. The quantum correlations perform a kind of magic trick. They encode all the chaotic information of the interior into the radiation, and they do it so seamlessly that no violent discontinuity appears at the boundary. That suggests entanglement isn't just weaving space. It might also be enforcing its rules. The laws of quantum information could act as a cosmic editor, censoring geometries that lead to paradoxes. They might allow only those patterns of connection that, on a large scale, result in the classical spacetime we experience. Pathological structures, wormholes that become time machines, naked singularities, glaring firewalls. They might be mathematically possible, but the quantum rules of entanglement could forbid them from actually forming. In a stable, consistent universe, the illusion of a smooth stage isn't an accident. It could be the outcome of a deeper quantum principle, one that insists on logical consistency across the entire web of connections. So the interplay is this. The phenomenon that threatens to shatter our classical stage might also be the force that holds it together. Quantum entanglement doesn't just build space. It might also be its guardian, ensuring the emergent geometry remains coherent, navigable for beings like us. The universe's most profound connections could be working behind the scenes, not to create chaos, but to preserve the predictable cosmos we call home. That guardian role of entanglement leads to a personal question: where do we fit in? The physicist John Wheeler had this idea, a participatory universe. Observers help bring reality into existence. It sounds philosophical, but with entanglement it becomes more concrete. In quantum mechanics, measurement forces a definite outcome. A particle in a haze of possibilities snaps into a specific state when it's observed. Now scale that up. In a universe where space emerges from quantum correlations, every local measurement, every interaction that collapses a wave function, doesn't just affect one particle. It sends a ripple through the entire web. It updates the global pattern of correlations. You measuring the spin of an electron in a lab doesn't send a signal to a star a billion light-years away. But it does participate in defining the relationships that, on a vast scale, constitute the geometry of everything. So observation isn't a passive reading of a fixed stage. It's an active interaction within the quantum network. And that interaction has geometric consequences. It helps solidify one thread of the tapestry from the infinite potential of the quantum loom. This doesn't mean we consciously create reality with our thoughts. That's a misunderstanding. It's more subtle. It highlights that the classical, stable spacetime we move through, with its clear distances and definite events, is a product. It's the outcome of countless quantum interactions and measurements that have happened, and are happening, across the cosmos. The universe we experience is a consistent story being written by its own inhabitants, from particles to people, through the simple act of interacting. The stage feels solid and independent because we are all, constantly, performing on it together. This final point distances space from its last vestige of fundamental status. It is not an observer-independent container. It's a dynamic, relational phenomenon, a grand consensus reality emerging from a sea of quantum potential, shaped by the very interactions it facilitates. We are not just living in the universe. We are participants in its ongoing creation, weaving the fabric of space with every quantum glance. The search is moving into a new phase now. It's not just about finding a theory of quantum gravity anymore. It's about building one where entanglement is the foundation, not something you add later. Where the equations for space and time and gravity are derived, not just assumed. That's the task, to show how the smooth, curving stage from general relativity naturally forms from a buzzing network of quantum links. There are several mathematical paths forward. One tool is the tensor network. You have this vast, interconnected web. Each node is a quantum state, and the lines between them are entanglement. Arrange these networks in certain patterns, and you can see a classical geometry emerge. A three-dimensional world coming out of the quantum data. It's like watching a 3D image resolve from a flat pattern of dots. These models show that distance and curvature can be calculated purely from the strength and pattern of entanglement in the network. Another path is the AD-S/CFT correspondence. It's a specific form of the holographic principle. It proposes a perfect mathematical equivalence. A theory of gravity in a certain curved spacetime is equivalent to a quantum field theory without gravity living on its boundary. In this dictionary, every phenomenon in the gravitational volume, every warp and ripple, translates precisely into the language of entangled quantum particles on the lower dimensional surface. It gives a blueprint for how spacetime geometry is encoded in quantum information. Other frameworks are different. Causal set theory, for example, it proposes spacetime is fundamentally discrete. A vast collection of elementary events. The smooth continuum is an approximation. And what defines the structure, what tells you which event comes before another, is again a pattern of relationships. Entanglement becomes a natural candidate for defining those fundamental causal links. These aren't just abstract exercises, they're workshops, drafting the new reality. And they will be tested. The next generation of tools is coming. More powerful particle colliders will probe the fabric of reality at higher energies, looking for any faint signature of spacetime's granularity. Space telescopes with new sensitivity will scour the cosmic microwave background. They'll map the large-scale structure, hunting for imprints of those first quantum entanglements stretched across the sky. And then there are quantum computers. They'll act as universes in a box. We'll program them with these new theories, instructing their qubits to entangle in the patterns suggested by tensor networks or holographic codes. And then we'll watch. Does a simulated particle within that synthetic system behave as if it's moving through a curved geometry? If it does, we'll have a working model. A demonstration that the recipe works. The ultimate goal of this whole journey is a set of equations. A theory so deep that when you apply its quantum rules to a vast system of entangled information, the familiar equations of Einstein's general relativity just fall out. They'd be revealed not as fundamental laws, but as emergent phenomena. The way temperature and pressure of a gas emerge from the collective motion of countless molecules. Success would be one of the greatest unifications in human thought. It would finally explain the magic trick. How the definite, classical world of planets and people and passing time solidifies from the shimmering possibilities of the quantum realm. It would crown entanglement not as a curious side effect, but as the true architect. The cosmic weaver whose threads spin the very stage of existence. The equations of that theory might not have distance in them at all. They'd be about a network of quantum correlations, a dynamic network, and from that network, the idea of separation would just to come out. It would emerge, the way wetness emerges from all those water molecules moving together. That's where this ends up. This whole path that started with spooky action. It changes what physics is even trying to do. We're not just plotting where things are on some pre-existing map. We're trying to read the relationships, the ones that actually draw the map. The universe isn't a set of nouns, it's a verb, it's relating, a process of relating, and space, the stage we call space, that's its performance. Its most magnificent emergent performance. We've reached a new view, a view where the stage isn't given, it's made, where the huge distances in the cosmos aren't empty voids. They're a living geometry that comes from connection. It started with a simple, spooky fact. Two particles can be linked, their fates intertwined no matter how far apart they go, that fact. Quantum entanglement was the first crack in the classical universe. It challenged the bedrock ideas, the ideas that defined reality for centuries, locality, the rule that nothing can influence anything else faster than light, and separability, the idea that objects in the universe are independent, that they exist on their own inside the container of space. Entanglement showed us those ideas are illusions. At the deepest level, the universe isn't a collection of separate things, it's a single, interconnected quantum whole. The speed of light is still the unbreakable law. For sending any signal we can control, any message, but the instantaneous correlations of entangled particles, they whisper of a deeper layer, a layer where here and there aren't yet defined, where relationships are primary, and the space between things is a consequence, not a cause. That's the radical shift. Space and time, the very arena of existence, they aren't the fundamental stage. They're part of the performance, an emergent performance. It comes from the fundamental quantum relationships. From entanglement, we're watching physics undergo a revolution. As profound as the one Copernicus began, we're not just moving the Earth from the center, we're questioning the nature of the center itself. The center isn't a place. It's a connection. As research advances in quantum gravity, in quantum information theory, we edge closer to a new paradigm, a set of equations where the smooth curvature of spacetime crystallizes. Naturally, from the buzzing network of quantum links, where a black hole's event horizon is understood not as a cliff in empty space, but as a boundary in a web of information. That's the promise, to finally unite the very large and the very small, under one roof, a roof woven from threads of correlation, so the next time you look up at the night sky, at the immense darkness punctuated by stars, try to see it differently. You're not looking out across a cold, empty expanse. You're looking at a magnificent, entangled tapestry. Every point of light, every stretch of darkness, it's a note in a cosmic symphony of connection. The distance is the music, and we, in our curious way, are beginning to hear the tune.